transforming graphs of functions. Well, first of all, it needs to be clear about what exactly is the graph of a function. The graph of a function is a picture of all the answers. Take a simple one. Here's a simple function. F of x equals x squared, just to make it a little more interesting than just x a straight line. To draw the graph of that means to work out all the answers for the different x's and plot those answers as y coordinates. In other words, if that's the function, then y equals f of x would represent the graph of the function. That's going to be the graph. That's going to give you the picture. That's going to give you the graph of the function. And the graph of that function would simply be, we'll go through the points. At 0, the answer is going to be 0, so the y coordinate will be 0. At 1, the answer will still be 1, 1 squared is 1. At 2, the answer is going to be 2 squared is 4. At negative 1, the answer is going to be negative 1 squared is back to positive 1. And at negative 2, it's going to be negative 2 squared, which is 4 again. We'll just stick with that. So the basic parabola would be this, where we'll just put in these other 2 points here. Obviously it goes on beyond that, we're just as if we're taking just the domain from negative 2 to 2. So this is the point 2, 4, and this is the point negative 2, 4, to give a couple more interesting points than just that single turning point. Then, what are the various transformations you can do to that graph? Well, they're going to be linear transformations, they're just multiplying and adding. So the transformations could be one of 4 forms. I could have y equals something times it. I could have a new graph which is the original one plus something. I could have a new graph which is going to be the original graph at some other position. I'll do the multiplication first. Or a new graph which is at some other position which is going to be a shift. There's 4 different things you could do by multiplying and adding, either outside or inside. And by that I mean this. Writing y equals f of x means that the answer you're going to plot, the value you're going to plot will be f, which stands for the answer you arrive at by applying that function, worked out at the position x. It's the answer at position, whatever's inside that bracket, at position x. So these different parts would mean, and I'll just rattle through them. So y equals a of f of x means I'm going to take my answer and multiply it by a, but keep my answers at the same position x. I'll do a set of them. So y equals 2f of x means the new graph, because it's not the same as the old one was y equals just f of x. The new graph is going to have answers which are twice the old ones. That's an important way to think of it. Y means your new y coordinate. That's like your new answer. It's going to be 2 times the old answer. That's what this part stands for, the part that was already worked out, the original calculation. It's 2 times the old answer, but at the same position, because it was originally worked out at x, at the same position. So if we was to take that a bit at a time, what would happen to all of those parts? Well, at 2, the answer was 4. Now at 2, the answer is going to be 8. So 2, 4 is going to go to 2, 8. 8 is 2 times the old answer. The origin, 0, 0, is going to go to, it'll still be 0, 0. Same position, x is the position. Answer, double the old one. Negative 2, 4 is going to go to double the answer, but at the same position. Double 4 is 8, which means you get a taller, thinner graph. Now, y equals a half f of x will mean you've got half the answer at the original position. So that all's going to happen is, at 2, instead of having 4, the answer will just be at 2. At negative 2, instead of having 4, it's going to be at negative 2. But still at the same position x, so that you'll get a shorter, fatter graph. Of course, normally that graph would go on forever, so that line would also be extending forever. And if that was a negative 2 multiplying it, then what that says is your new answer will be negative 2 times your old answer. That's the old answer, the original calculation at the original position, which is still x. So the new answers will just be negative 2 times the old ones, which means instead of 4 it will be 8, but negative 8. Instead of 4 it will be 8, but negative 8. It will be upside down, looking like, again, an expanded upside down graph because of that negative. Then, y equals f of x plus 2 means the new y coordinate will be the old answer, the original y coordinate, still at the original position x, but moved up 2. So every point is going to move up 2. All the answers will be increased by 2. Still at 2 instead of being at 4, the new answer will be at 6. Instead of negative 2, at negative 2, instead of being at 4, it will be at 6. At 0, instead of being at 0, it will be at 2. So you get the graph moved up 2, still with the same shape. Or, if it's subtracting a number, then that simply means the same as before. The new y coordinate will be the original answer, still at the same position, only drop 2. 2 off of all of the answers. Instead of 4, down to 2. Instead of 4, down to 2. Instead of 0, down to negative 2. So you get the graph with the same shape, drop down 2. Then, putting it together, having this transformation simply means my new answers will be, and here are the original answers, will be the original answer doubled and 3 added. So that's stretched by 2 and then shifted up 3, but still at the original positions. So that I would have at 2, my new answer would be 2 times 4 being the old answer, which is 8 plus 3 is 11. Same here, that will be 11. At the origin, it will still stay at 0, but the new answer will be 2 zeros is 0 plus 3 is 3. So you would get this for the new graph, where it's been stretched to twice its height and lifted up 3. If it says y equals f of 2x, then what that's saying is the original answers aren't going to be changed. There's no alteration to the original calculation. What's happened is you're plotting your answers from a different position. That's the original position, and you're going to be moving it just to x, which is the same as saying this. At x equals to 0, if I just put this down slowly underneath, at x equals to 0, I'm going to plot the answer which was at x equals 2 times 0 is 0, so that just stays there. At x equals 1, so at x equals 1, I'm going to use the answer for 2 times 1. So I'm going to take 2's answer and move it back. So that's actually going to be up at 1, 4. At 2, I'm going to plot the answer for 2 times 2, which is 4, which means I'm going to take 4's answer, which was 16, and move it all the way back. Same at negative 1. At negative 1, I'm going to take the answer for negative 2, but plot it at negative 1, so that would be that 4 shifted back, which means that for this one, the whole graph's going to be squashed up. It actually does the opposite. It doesn't double as it expands along the x direction, it compresses. Notice there's no change to the answers. The answers stay the same, they're just getting put into different positions. In this case, they're getting squashed. Or, algebraically, you could think this. F stands for the original answer, unchanged. So the range of answers will stay the same. But 2x is where you're going to find those answers. That was the original position of those answers. You could call that original position x naught, which means that 2x was the original position, so x, like y, being the new positions, would be a half of x naught. In other words, all the x coordinates are being halved. So instead of 2, 4, doing this would give you still 4, because there's no change to f, but half of that's 1. Still 4, but half of that's -1. And the same for y equals f of a half x. F, nothing's happening outside of f. F's a complete. Once you do f of something, that's the answer worked out. So you've still got the same set of answers. There's no change to the answers. They're just going to move into different positions. Well, what's going to happen in this case? Well, half of x means that the original position was a half x, so the new position's going to be double wherever it was. Or you could think that at 1, you're going to plot the answer for a half. So that's the smaller answer is going to spread out to 1. At 2, put 2 into the formula, you're going to plot the answer for 1. So one answer is going to move out to 2. At 4, you're going to take 2 answers and spread, the whole thing will spread out. Well, you could just use that formula there. The new x coordinate is 2 times the old x coordinate. So you get this. Same heights, no change to the answers, it's just spread out. Because this says f, nothing's happening to it, same answers, what's happening inside? Well, half of x means that you're going to have double. You can always just think of it simplistically as the inverse of what it's saying. But of course it is the inverse, because to get x on its own, you've got to do the opposite. So it's going to be spread out, it's going to be a doubling. Everything's going to move twice the distance away from the origin that it used to be. Or f of -2x. That'll be difficult to see in this case because it was symmetrical about the origin to begin with. Maybe if I had the 2 halves coloured differently. Then -2x means at x, like at 1, I'm going to plot the answer which used to be, this is the original position, at -2. So I'm going to take -2's answer and move it over to 1. So 1, it would be -2 answer. 0 will still be the same because that just still comes to nothing. At -1, I'm going to plot, it says the rule here is use the function on -2 times each of the x's. So that'll be -2 times -1 is 2. So I'm going to take 2's answer. So it's actually going to move it over. The graph would actually end up looking like this. I'll just use the black for that. It's been squashed up, it's not quite so obvious because of a symmetrical parabola, but flipped over. The graph would be flipped over, that's the effect of the negative. The effect's happening inside the bracket, so it's changing the x positions of the answers, but not changing the answers. The answers stay the same. Squashed up to half the size. Y equals f of x plus 2. The effect of that would be the answers will stay the same, so the answers will still be 0s and 4s, no change to the range. The change is taking place in the starting positions. So where those answers are going to appear. And what this says is, at 0, if x is 0, I'm going to use the answer for 2. So 2's answer gets moved back to 0. At 1, I'm going to take the answer from 3, so it's going to move back. At 2, I'm going to take the answer for 4 and it's going to move back. All the points will move back 1, so you would get, 2, so you would get the graph moving back 2 places. You can just think of it simplistically as do the opposite whatever it says inside. So leave your answers alone, but shift them all back 2. Or you could do it algebraically by saying, well, what happens to the various points? What happens to 2, 4? Where does it go to? Well, the answers aren't changed, so the answer's still 4. Those were the y coordinates. The y coordinates were the answers. Where's your new answer? Well, x plus 2 was the original position. So x plus 2 was the original position 2, which means the new position is going to be take away 2, which is 0. So 2, 4 should go to 0, 4, going back 4. And the same for the other ones. Or y equals f of x minus 2. In this case, the graph should still have the same answers, 0s and 4s, but the positions will be different because they're going to be, just think of it simplistic as the opposite of that, shifted forward 2. Or you could work it out, where would the point 2, 4 go? Well, the answers are staying the same, so they're still going to be at 4. But if that's the original position, those answers were found at this place, which was at 2, so the new answer will be found at 4. so it shifts forward 4. Same for the other ones, so you get the exact same picture, only it shifted forward 2. No change to the answers. Or a combination. In this case, same as before. No change to the answers, because nothing's happening after you've carried out F, so it'll be the same range of answers, but the positions are going to be changed to find where the new answers are going to go. Well, it's the same as the old answers, because that's where you had the original positions. 2x plus 3 was the original position. Remember, it's the inverses of these. In fact, it's the inverse operation. So it should be everything moves back 3, and then wherever the new position is, you then squash them all up towards the origin by 2 times. So it becomes half the width. Or just do it algebraically here. It's going to be x naught minus 3. So x is going to be a half of x naught minus 3. Or splitting it, half of x naught minus 1.5. So it doesn't actually move back 3. It only appears to have moved back 1.5 as far as any of those points with no height's concerned. Or you could just do that algebraically. 2, 4. Where does it go? Well, no change to the answer. Nothing happening outside that box, so it's still at 4. Where will this new answer be? Well, the original position, which is what it specifies in here, was 2. So the new position will be, take away 3, negative 1, will be at, then divide by 2, negative a half, will be at negative a half 4. What about the origin? That's one of the significant points, because it's a turning point. Usually when you get these questions, it's usually just the turning points that you need to find in the transformed ones. 0, 0, where will it go? Well, no change to the answers, still be at 0. That was the original position. So 2x plus 3 is the original position, so 2x will be negative 3, so x will be negative 1.5. It will go to negative 1.5. And same with the other one. Where would negative 2, 4 go? Well, it'll still be at 4 because no change to the answers, but what would happen to negative 2 under that? Well, the original position, the original answer at the original position was negative 2, because that's what it was to begin with. Where's its new position? Just like that, y stands for the new position for y. It's going to be, take that away, negative 5. So x is negative 5.2, negative 2.5. So the graph would look like this, much as you'd expect. The 2 times x means it's been squashed, so it's only half its width, but it's not moved back 3. It's only going back 1.5. Because of that inverse effect of that, because you have to think of the opposites all the time, the opposite of each of the things in the bracket. And then finally, what about one, put them all together, like this one. So what would the graph of this look like if that was the original function? Well, you can see there's 3 parts to this. There's the amplitude, there's the change to the height, you would call that an amplitude change. There's an addition to the answers, that's like a vertical shift. There's a change in positions. It's quite handy to think of that like a frequency change, because if you're multiplying, if that was a 2, everything gets squashed up. It's like sound waves getting compressed. And so if it's a half, it's like them getting expanded. You can think of that like the frequency change, but I haven't put anything, I haven't put in a separate horizontal shift. So what would happen to this? It's going to be twice the height, upside down, shifted up 5. That's where the new answers are. Twice the height, upside down, shifted up 5. That's my set of new answers. Where they're going to be? They're going to be double where they were originally. So it's going to get expanded across the way after that. You could sketch it that way, or you could take the significant points and just do this to them. I'll take them in order to start from this side. So negative 2, 4, where would it go? It's important to remember there's 2 parts to this. That stands for the new y coordinate. There's the original answer, and there's the original position for those answers. So my new answer is going to be 5 minus 2 times my old answer. So if I was to spell it all out, this is going to be 5 minus 2 times my old answer. And in here, the original position was negative 2. So I could say a half of x was negative 2, which means it's going to go to 5 take away 8 is negative 3. And if a half of x is 2, that means the new x will be, take 2 across and multiply, negative 4. The point 0, 0 where will it go? Well, answers. The original answer was 0. 5 minus 2 zeros is 5. Where's it going to be? Well, the original answer was at 0, so the new answer is going to be 2 zeros and still 0. Where will the point 2, 4 go? Well, if the original answer is 4, F stands for that, then the new answer, Y, is going to be 5 minus 2 fours, 5 minus 8, so it's going to be negative 3 again. Where will it be? Well, the original position was at 2, so the new position must be at, take the 2 across and multiply, must be at 4. And then put it all together. And you get this. So what you've got is, it should be twice the height. Went from 0 to 4, which was a difference of 4. Now it's going from negative 3 to 5, it's a difference of 8, so it's been stretched to twice the height. Negative means it's now upside down. 5 means once that happened, because it should have been upside down throughout, it's all been shifted up 5. There it is, going through 5. And then what about the positions of them? Well, everything's going to be double where it was to begin with, so it's been spread out to twice the distance, but still about the origin, so the origin itself doesn't change. Right, a quick visual recap. Right, we'll display the results on a wee television. So let's make a screen, and then there's a wee box that holds all the gubbins, and there'll be 4 controls, the same as those 4 different operations, and a wee secret button. Right, I'll need a set of axes so you can see how it moves about. Then for this first button, let's just get a wee graph in. So there's a graph. Now the first control here is going to change the vertical expansion. That would be like the amplitude of it. That should stretch up and down, much like this. Up it goes, and if it's a fraction, down it goes. The next control is going to affect the vertical shift of it, adding, subtracting numbers. Up it goes for adding, down it goes for subtracting. The next little button here is going to be like the frequency. That's going to affect it across the way, squashing it though. So as you turn it, it squashes, and the opposite with fractions, it expands it. And the last button is going to be a horizontal shift, again doing the opposite. As you add to it, it actually goes backwards, and as you go backwards, it goes forwards. So, what was that? What about if the amplitude was negative? We'll put a wee negative button here. Press that button, and it pops upside down. Positive answers become negative answers. And the same as before, that'll expand them. Back you go. And same with the frequency. If that was a negative multiplying number, pop, it reverses side to side. And again, it does the opposite, expanding and contracting it. Now, what's this wee secret button at the side here? Well, that's not in the higher course. This is the modulus button. It's an absolute value. It turns negatives into positives. So pressing that, pop with all the negative parts, flip up into positive parts. So there we are then. What have we got? Let's call these buttons A, B, C, D, the same as you had before, so that the linear transformation of a function could be made up of these 4 parts. A, the multiplying number, which expands it, B shifts it, C compresses it, and D moves it back and forth. There. As a final, more involved example then, here's a function. What would the graph of this transformation look like? Make it a half of, we'll put alterations everywhere, 4 minus 2x minus 1. What would this graph look like? Well, first of all, we need the original graph. What about y equals f of x itself, the original graph? That would look like this, where the turning points could be found by differentiating that equal to 0, and where it cuts the x-axis can be found by equating that to 0, and then solving that, factorising and solving it. But in general, if you're doing the higher, this graph would already be given. The other thing is, these points on the x-axis may well not need to be put into the answer. If they transform off the x-axis, they'd no longer be interesting points. The only interesting points in the graph are these turning points and where it cuts the axis. But I'll mention that bit after, but where it cuts the axis. So what does this do? We're using a little transforming television. There's the graph. What are the different operations that are going to happen to that graph? Well, there's 4 of them. The first bit's the amplitude to half. It changed the amplitude to half, but it's still positive a half. So that would be the first thing that we would do, because you carry out the normal rules of operations here. On the answer, it's multiply and then add. Within it, remember, it's the reverse of the operations, so it's actually going to be subtract the 4 and then divide by the negative 2, but in order. So there's a half operating on it first. So if I turn that back to a half, then it all shrinks by a half. Vertical shift of -1. So if I turn that to -1, then it shifts down 1. I've lost these interesting points where it cuts the x-axis. Where it cuts the y-axis is still there, because that's now at -1, having dropped -1. Next would be the 4. A shift of 4 would have the opposite effect, like this. So it's all going back 4. Oops, it's off the scale here. I should have made that picture a bit smaller. Then, the -2. So a frequency of 2, but make it negative. So first of all, the negative button, and it flips over. Then frequency of 2, then squashes it all up by 2. So I know where my turning points have gone, but I've lost those other interesting points where they're going to cut the axis. I'd have to do that by some other calculation. But you wouldn't have to do that in the higher. In the higher, it's just be a case of where would the new turning points be. Right, doing that by the calculations then to arrive at these figures. So algebraically, what would happen? Well, the only two significant points are these turning points. What would happen to them? Well, the point -2, 16 would go to, like, what would happen to it? The answer, the new answer is half the old answer, which is this, the original answer. So I'm doing a half of the 16, I could just spell it out. A half of 16, take away 1. What about the new position? That's this x here. Well, the old position is going to be -2. So the new position is going to be, quickly solve that just in here, 2x equals, take the 2 across, is 6, so x is going to be 3. The new answer is going to be a half of 16 is 8, take away 1 is 7. So that point is going to transform to the point 37. What about the point 2, -16? Where will it go? Well, that's the old answer. The new answer is a half of the old answer. So it's a half of -16 take away 1. That's the old position. The new position will be this. 4 minus 2x equals the old position. So that means the new position is going to be solving that. 2x equals, take the 2 across and subtract is 2. So x is just 1. And half of -16 for the new answer is -8. Take away 1 is -9. Now, those are the only points, only interesting points I know for certain in my new graph, and that would do for a sketch of it. Because these other points, these 3 points on the x-axis are going to get transformed off of it. If they were going to get transformed to a point on the x-axis, I would use them. I'll do it for just one of them, just out of interest. 0, 0. Where's that going to go? Well, the same thing. It's going to be a half of the answer 0, take away 1, so that's -1. So straight away it's dropped off the x-axis, so it doesn't matter where it goes. I've got an uninteresting point floating about on the graph off of the axis somewhere. We can always carry on with the other bit. What would this be? That would be 4 minus 2x equals 0 for this one. 4 minus 2x equals 0, so 2x is 4. So that would go, the origin's going to go to the point 2, -1. And suddenly with those two, they're going to move off the axis. You could do the exact same calculation, find where they're going to go to. Which means that the graph then would look like, so this would be it. Where the only interesting points are these two here. The 2 turning points that I got straight away from the original one, because these other points where it cut the x-axis has now dropped off and become uninteresting points. The other interesting points would be where does it cut the axis, but I can't get them directly by a simple transformation. I'll mention that one in a minute. I could get that one. That's not too bad, to find where the new graph cuts the y-axis, because that cuts the y-axis at the new x, when x is 0. So I could do that quite quickly. I could work out the new y-coordinate of where it cuts the y-axis by just doing a half of f times 4 minus 2 times, and just put 0 into that, -1. So that's going to be a half of f of 4 take away nothing's 4, so f of 4 minus 1. So that's a half of, put 4 into the original function, and that will be 4 cubed minus 12 times 4 minus 1. So that's a half of 64 minus 48 minus 1, so that's going to be a half of 16 minus 1, so that's 8 minus 1, which is 7. So I know the new graph will cut at 7. However, finding where the new graph cuts the x-axis is a little bit more complicated, and you probably wouldn't be asked for that. To find where the new graph cuts the x-axis, that's like saying the new y-coordinate's got to be 0, in which case I'd have to solve this. A half of f of 4 minus 2x minus 1 has to equal 0, which means I've got f of 4 minus 2x equals 1, then doubled it, equals 2. And what does f do to this if it operates on it? It will be 4 minus 2x cubed minus 12 times the thing it's operating on. 4 minus 2x equals 2. I'd have to solve that equation, which would probably have pretty nasty little answers. You can either multiply that out into a big cubic equal to 0 and try and factorise it, or you could use a change of variable. But as far as the higher is concerned, you wouldn't be doing that at all. It would just be, where would the interesting points go to? And possibly, because that's not too bad, where does the new graph cut the y-axis? There.